Hello, everyone, and thank you for attending today's webinar, How to Optimize Backgrounds for EBSD Analysis on Multiphase Samples using OIM Analysis version 8. Before we begin, I would like to cover a few housekeeping items. At the bottom of your console are several application widgets that you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer those as they come in during the webcast, but if a fuller answer is needed or I run out of time, you guys will receive an answer via email. We do capture all the questions as they do come in. A copy of today's slide deck and some additional materials are available in the resource link. It looks like a green folder. You can expand your slide area by clicking the maximize icon or by dragging the bottom right corner. If you have any technical difficulties, please click on the help widget. It's the question mark icon and covers common technical issues up in the top right corner. And an on-demand version of this webcast will be available in approximately 1 day after the webcast and can be accessed using the same link that got you here. So now I'm going to introduce myself. Quite a few of you guys already know me, but I'm Sean Wallace. I'm the EBSD application engineer here at EDAX. I've been here a little bit over 3 years now. My background is geologic. I come from the University of South Carolina, where I did my master's degree. And then after that, I was at the American Museum of Natural History, working on meteoritics to understand the origins of the solar system. Of course, doing all that work leads you to a lot of instrumentation, including things like EBSD, electron microprobe analysis, and all kinds of mass spec. So with that, I'll go ahead and start the webinar. So the reason I'm kind of doing this is, OIM analysis has been out there for a while now, but I'm really starting to use it in more of the features every day. And with that, you start finding little things in there that might not have been in there on purpose, but really kind of change how you collect your data, how you play with your data, and really something to think about, and it really kind of affects my day-to-day use of what I'm doing. So one of the new features that in this is not just the data processing, but we've added a lot of the indexing engine inside of the software itself. So this allows us to do a lot more options and post-processing patterns, especially when combining with the partitioning functions. And the partitioning functions are really kind of a neat way of pulling apart your data to get to the subsets that you want to play with. Now, with this pattern indexing, you're able to view and reindex EBSD patterns within the OIM mapping data set. You can reindex the data sets using either the Huff peak information or your saved patterns. I'll probably say this 3 or 4 times, but I'm now routinely saving patterns for all my data sets. And if I'm going to do a lot of this reprocessing, I need those saved patterns. No saved patterns, I can't play with the patterns themselves, and because of that, a lot of this is moot. But if I do have those saved patterns, I can go back, redo the Huff itself, change the processing, and I'll basically start from scratch. I can also use this data to reindex by a single point, by the partition level, which I'm going to talk about later, or of course the complete data set. Now when I'm doing this work, I also have chi-scan and NPAR available to me. And of course I also have my batch indexing is also available with full chi-scan, NPAR, everything else I'm doing. So I can go ahead and take this information and just do the same thing over and over and over again if that's what I'm doing. Now, why would I want to do some of this reindexing? Well, I can correlate the patterns with the microstructure a little bit, so I can say, okay, here's what's going on. And then I can also adjust the phases. I can change the band detection, so I can actually fiddle with the Huff quite a bit. And I also can fiddle with the calibration value if it's a little bit off. I would say for the average user, the calibration is not that important because it's done by the system ahead of time, and you don't need it. But for somebody like me who's getting customer samples from all over the world, data sets, it can be really useful. But really, what I can do with this is also I can optimize the image processing, and this is going to be kind of what I'm focusing on today. I'm going to create new backgrounds and also apply additional processing. And just a little bit about chi-scan while we're here. And let's go ahead and, chi-scan is a way of, looking at and using the EDS data to help us improve the EBSD phase differentiation. And of course, it allows for accurate differentiation of crystallographically similar phases or just difficult material in general. So again, if I'm doing geological material or multi-phase samples where the chemistry is different, I can use the chi-scan as an initial filter and go ahead and do that. Now, chi-scan, of course, is its own little thing. I'm going to basically show you in this how to not use chi-scan to do chi-scan, and I'll show you about why and how that's done. Of course, why would I want different backgrounds for different materials? And this is kind of going to get to the real kind of the gist of this presentation is, well, a standard background can be used to great effect on single-phase samples. So let's say I have my nice standard nickel sample. The diffraction strength for the entire material is pretty much the same. And because of that, the background is pretty much the same. Now, if I have a multi-phase samples, then I can start running into issues because they can have way different diffraction strengths. Let's say I'm dealing with ceramic, and some of them have, rare earth elements in it. Well, that increases the Z number. Increases Z number equals usually a higher backscatter coefficient. And because of that, I basically have more electrons flying back at me, which I usually have a brighter signal. But right next to that, it might have something that's much lighter weight. And because of that, I'm going to have less scatter. I'm going to have less signal in general. And if I try to take the same background from those, my contrast can be lost. And because of that, I can either have issues indexing one or other of the phases I'm doing at the same time. But let's go ahead and backtrack a little bit and ask about why backgrounds are important to begin with. But before that, I'm going to ask a good old poll question for you guys. And the poll question is going to be, what kind of background do you usually use when you're doing your samples? And of course, the options here are I use the default background, a nice standard background that you kind of click the optimize button and it does it for you. I sometimes change to the enhanced background. It gives you a little bit better contrast. Or I actually occasionally use my own background, where I actually make a custom background to fit my needs using the custom image processing. I'll just go ahead and let you guys answer that question a little bit more, and we'll go ahead and see what we do. Nowadays, honestly, I almost always use a custom background myself, and I'll talk about why that is. For most materials and single-phase materials, the default does work perfectly fine. But if you're doing more complex samples or multi-phase samples, it can be sometimes better to use different ones. So let's go ahead and look at our results. That's pretty much about what I expected. About 50% of you guys use your standard default background. And again, if you're doing single-phase samples, that's going to be pretty common. I sometimes change the enhanced background. That's good to see that you guys are aware of that option and use it. And again, that can give you better contrast. It does a dynamic, believes in subtraction on top of it. And again, it just helps increase the contrast a little bit. And of course, there's users out there who do make their own background, which again can be highly useful for difficult samples. So let's go ahead and talk a little bit more about backgrounds and why I do them. So this right here is a raw pattern. I can see it's a raw pattern for a couple different reasons. One, very low contrast. Now on top of this pattern, the actual bands themselves are superimposed across that intensity gradient. So I can see there's a big band contrast between the middle of the sample and the outside of it. Now this can make it a little bit difficult for the Huff to do its job and find the middle of the lines because of this lack of contrast. Let's go ahead and take a quick look at this. Here is our Huff space. And there I can see these little peaks, little kind of areas that kind of stick out to me, but they're not very well defined. Now, if I go ahead and use those peaks, we can see here that I've found quite a few of those. But if I go ahead and do a background on this, it can go ahead and give me a little bit better idea of what it's doing. So what we can do with this is we can essentially look at this and remove the lovely, the background on top of it and get a lovely pattern off of this. So that's why we're doing this, is we're trying to increase the contrast, let the Huff do its job better. So with that, we go ahead and actually look at what this pattern looks like in 3 dimensions. And I think this is kind of a neat way of looking at your thing. So here's the pattern. Let's go ahead and look at it on background corrected. And let's go ahead and look at it in 3 dimensions. So there's your 3-dimensional aspect of the pattern. And what you're looking there is, of course, the peaks and the valleys. So again, it does a really good job of showing the gradient of the pattern. Again, you can see it's really brighter in the center. That's where your pattern center is. And towards the outside, you can see it gets weaker. Now, again, what the Huff is looking for is those bright peaks surrounded by dark valleys. And again, that's the three-dimensional aspect of the data. So if I background correct it, it goes ahead and gives me a little bit more of that contrast that I need to do it. So background correction is applied to minimize these effects. Now, I go ahead and do that. I turn that pattern into what that pattern looks like there. So again, it's now flat fielded. I can now see the contrast of the bands better. So I'm expecting the Huff to do a better job. Let's go ahead and look at the Huff itself. Now I can see those spots stick out much more strongly, and the Huff is able to easily find that. Now, in this case, I believe all the bands, I think one of them was initially a fake band with a bad contrast. Now, our indexing method can usually get rid of that, but in this case, it's always best to start with your best Huff. And in this case, again, we can see the Huff is doing a great job. Also, you look at the Huff, you can see there's another 5 or 6 lines it could find because the contrast now exists. Let's just go ahead and look at that before and after. And again, you can see that the bands aren't really changed all that much, but because of the increase in the Huff, a little bit better precision, and I can find more of them much more easily. So again, this is the kind of the purpose of the background, is to help the Huff do its job by making the contrast brighter in the sample. Now, the standard background essentially does a couple things. One, it scans the sample. So it scans over the entire area, takes some patterns, averages about 25 of these together, and then removes those average patterns from the actual image. And again, that's when you get that. Now, the fixed background typically consists of 25 or more patterns. The time it takes would be based on your integration time. And of course, this is usually connected. Sounds like a lot of you guys probably do this automatically using the default camera optimization settings. Of course, I can do this manually. But one of the things to always remember is you want your EBSD or your SEM to be fast scanning. So if you're doing a really slow image, your background can be one single area, and that because of that you can go ahead and get the actual lost my train of thought there. You can go ahead and make sure you get a more than one grain, because you want to have multiple grains when you're doing this. So again, we want to make sure that we're doing this. You also want to make sure that you're zoomed out to get enough grains, because again, if you have 3 or 4 grains, you're going to go ahead and see this. So now, again, 25 patterns cannot be enough sometimes. So some recent work from, I believe it's the CMU group, including Mark DeGraff. Recently, I've been doing a lot of work with this dictionary indexing kind of stuff, and I've been looking at backgrounds using that. So here they actually looked at 25 patterns over the entire orientation space, and because of that, they looked at it and say, okay, is there enough blurring at 25 patterns? So here at 100 patterns, you can see that you're pretty well flat fielded artifacts. And at 25 patterns, you actually can have a little bit of an artifact in the background itself. So there we can kind of see what's going on. Now, so in general, when comparing these, we want to make sure we have enough, but we want to make sure we're not taking too long. So in general, again, the default works. It's also depending on how your grains are, grain sizes, and how fast you're scanning. But in general, again, you want to make sure that you have enough background to get rid of them. So often it's best to make sure that when you're initially setting up your scan, that you have no visible images in the background when it's basically scanning. Here again, you can just quickly see how this kind of works itself out. So again, it pretty drops off pretty quickly after 100 patterns or so. So again, just something to consider is how many points you do have in your background, how fast your system's scanning, et cetera. Now, the other kind of background I can do is called a dynamic background. Dynamic background is a little bit different than a static background because it actually takes the pattern itself and blurs that pattern and then subtracts it from itself. Because of this, it's really useful for things like single crystal materials, rough surfaces, and multi-phase samples. Now, a couple different things to think about here is, one, this is much slower than a static background. Why? Because it's actually doing this for each pattern. It collects the pattern, it runs the blur filter on it. from adding an basically extra image processing step, it takes a while. The other thing to consider here is that any defects in my phosphor screen are still going to remain. So if I have damage to my phosphor screen over the years of use, or just on accident, that the defect tends to remain if I'm using just a plain static dynamic background. And of course, this can be used together with the static background to get away with things like that. So from that, we we use these backgrounds, and then the background again can actually change the patterns quite a bit. So here you can see a single pattern on the far left there by itself. You can see as detected, basically fresh raw pattern. Also standard background subtraction, again better contrast. Again, you look at the dynamic background subtraction, you can see that some of the contrast is lost because of the way it works. And again, this is one of the things where I think the newer methods can really kind of help is for, again, multi-phase samples, we often want to use a dynamic background to help us with the multi-phase nature of it, but at the same time, I can lose contrast. And of course, if I start adding these together, we can see that, I have either better or worse contrast, and going, all but adding all these together, we can see again, it's just kind of a game of what's good, what's bad for your sample and for your materials. So here we can see, a little bit more afterwards by doing the Huff. You can see again the contrast can be added or removed depending on what you're doing. Now, these recipes really do affect the band contrast, the contrast of the band themselves by the Huff itself. So again, we need to look at this and think about this when I'm collecting it, because in the end, this is one of the important things about EBSD. The patterns can be ugly. I can show you data sets where you can't see a pattern in there, but the Huff nails it. Sometimes I can show you patterns that look relatively pretty, and the Huff might have problems. So the key here is not your eye so much as the way the Huff sees it. So the Huff is the one that has to find the lines, not your eye. So again, we're trying to do this to make sure the Huff is the one that can do this. Actually, we just got a good question here on slide 17. What is your target? It's kind of a moving target of how many. So slide 17 is the one with the amount of backgrounds. So it's going to depend on your material, and it's also going to depend on your SEM settings in general. Your target usually is to make sure that you have no artifact from the background inside of the actual pattern. So if you have a bad background, what you often will see is a kind of a latent pattern kind of forming in the background that looks reversed from the pattern itself. So you'll see that it's kind of dark in the middle and light on the edges of the bands. And again, you kind of see this in your data. It's usually not that big of an issue. There's a slight artifact in there, but if you get a strong artifact, it will affect your data pretty strongly, especially with a big grain, because then you'll be extracting or removing that pattern from that large grain. That large grain is going to misindex by itself. So again, it's kind of a moving target, and this is kind of going to actually get to the heart of what I'm going to be talking about towards the end here is before you do EBSD scan, you have to think about all these things. But what if I could think about it afterwards and not have to worry about the background so much ahead of time? And that's kind of, again, that's the kind of getting the meat of this talk. So again, here I can go ahead and play with these, and again, strong patterns can be indexed in general with all these options. So in this case here, we can see that even though no background one, I can index this. And these are all perfectly indexable. But if I do have deformed samples, the patterns are going to blur, and then it could be issues. So in this case here, no background, I couldn't really do it. And even some of the dynamic ones might have issues. So over there in the bottom left corner, dynamic subtraction, and dynamic division, both there's very, very, very weak pattern intensities, and because of that, I could have issues. So this is going to be a deformed Martin site, by the way. So again, I can do these fixed backgrounds. I can subtract them. I can divide them. Again, plain background subtraction works great for homogeneous samples with or samples with backscatter coefficients that are very much alike. And of course, background division tends to work better for large intensity gradients, multi-phase samples, gives you a little bit higher, can give you a little bit higher contrast, but also again it can lead to a little bit of noise and noise bands because of it. So again, it's just kind of this tricky process of, okay, I have to choose the background before I go. And we can see these backgrounds actually have a lot of effects on my data itself. So this is going to be the same data set collected as raw, and then also through the different background techniques. So here we can see that, this is a good sample of this. Again, it's deformed, tensile deformation in this case, which also gave us some topography. So strong deformation in this case gave us great big differences in what we call the IQ map. An IQ map is kind of a band contrast map showing us basically how much information I have in the pattern. And then of course we can see the background division kind of stuff gives us a good difference between things like the topography or shadowing or deformation kind of things. So again, up there on the top I have no background. I have okay contrast. But if I start piling these on, I can actually make worse contrast by doing like a straight division. Or if I do both a division and a dynamic subtraction on the bottom right there, I have very, very strong contrast, which is kind of what I'm kind of expecting to see in samples like this. But again, the real question about this is, how does the background affect my data itself? And that's what we're going to talk about now. So again, there's the IPFs that can we actually look at this, and this is what the IPFs themselves look like. So again, in this case here, we are looking at the data sets basically raw, running them through the indexing routine. Here I can see with no background, very, very like speckly areas with some data. If I do a background subtraction, I can see I'm starting to get better data. I'm getting more coherent grains, but still quite noisy. If I do a division, again, very, very speckly. And I shouldn't be happy with that data as collected, as ran with that background division. Dynamic subtraction, again, I'm not getting that great of data from what I want. Let's go ahead and do a dynamic division. I got nothing. In this case, the dynamic division can be very low contrast. The Huff has issues. In the end, I don't get good indexable results. Now, standard subtraction with a dynamic subtraction. I can see in this case I'm getting a relatively, out of all these data sets, probably the best one so far. And from this, I can go ahead and look at the next one. And here you can see again, I'm getting relatively good data. And then the final one, again, it's okayish. So now here it kind of gets to the setup of, how do I know this kind of ahead of time? But let's go ahead and backtrack a little bit, and let's go ahead and filter out the bad data, so to speak. So here I've taken those initial IPF maps, and I have removed the data that has a CI less than 0.1. So a little bit of background information here. The CI is what we call the confidence interval. The confidence interval is basically a measure of uniqueness. It is how unique my first solution is versus my second solution. And usual, the 0.1 value is kind of like the 90% correct cutoff value for most of our work. So around here, again, I'm 90% confident that I have the right orientation for each individual pixel. So here I can see with no background, I actually have a relatively small percent of the area that has a very high CI. And again, a lot of that was misindexed or not indexed at all. If I do a subtraction, again, I can see it goes up. Division, kind of the same. Dynamic subtraction, again, it kind of goes down. With the dynamic division, with the no contrast, only the stronger grains are really giving me any sort of information. So again, very little areas with high CIs. And of course, the final three is a little bit more of a custom background, meaning subtraction and division together, or division and division together. Give me better indexing data, but I'm still missing quite a lot. And if I look at the phase maps in this case, again, I can see I'm missing quite a bit of data. So the issue is I really have to sit this background before I collect my data, and I might not be quite happy with the data when I get done with it. So I can see that this, again, has a major, major effect on my data, but I have to basically choose a background before I start. Well, what can I do about that? And that's, I think, is one of the keys of some of the new toys in OIM analysis that have really kind of changed again, how I collect my data itself, because I can actually choose and manipulate that background after I've finished now. And because of that, again, it's really changed how I've collected data. And I've gone away from even collecting data with backgrounds recently. Now, why? Well, I can change this after the fact. But, you know, the one thing to consider here is, again, I need patterns. And if I have the patterns, I can play with them. The other thing to realize is that we save the pattern not as collected, but as processed. So if I have a background already done, we save that with the background done. Now I can still throw another background on top of that, but just consider that in general, that you can, you know, if you do have a background on it, and you do some sort of fancy background, maybe a dynamic one, gives you a little contrast, you know, you're basically starting with a pattern that's not that great to begin with. Because of that, you might have issues trying to doing some of this post-processing. But in this case here, you know, again, I routinely will either collect data either with no background nowadays or with just a standard background and fiddle with it after the fact. And again, here I have, you know, the ability to essentially play with that background because we built additional tools and have all of our filtering and other processes built in to the OIM Analysis software now. So here I can see the pattern I was collected on the left and what I've done to it on the right. Now, is that better or worse? Now, here we're just kind of playing to show what we could do. But again, I can turn these on and off. Order does matter, of course. If I do division before subtraction or subtraction after before division, it'll give me different results. But of course, here we have multiple options that do you know, quite a bit of different things. And again, these are something I would tell you to kind of sit down and play with. The best way to learn this kind of stuff is by doing. So just sit here and go ahead and click on this, and I'll show you where you click on this in a bit. Again, there's a whole bunch of different tools in here built in to actually play with and get the contrast and the patterns that we need after we've already collected the data. Now my next actual question for you guys is, I want to know what you guys run. So do I usually run a single phase sample? Do I run a multi-phase sample with very similar chemistry? Basically saying I'm not going to have you know, any different contrast kind of in my sample. Also, if I have multi-phase samples with very different chemistry, or you know, maybe you've never actually run an EBSD sample, you're just here to kind of learn what EBSD can do. So that's one nice thing about these webinars is we get a little bit of, you know, a little bit of everything here. Sometimes we get people who, you know, run the same thing over and over again, and it's a nice simple middle. And then I get people who have 14 phases in one sample and have to, you know, do quite a bit of work to get the best out of their data. And some people are just kind of learning what the technique can do and if it's right for them. A couple more seconds for you guys to, you know, click your button. Let's go ahead and see what our results are. So about 22% of you guys are using single phase samples. Sounds about right. I know there's companies out there that, you know, all they do is steel or single phase aluminum. So that's pretty common. Multiple samples with multi-phase samples with very similar chemistry. Again, about what I suspect. Of course, multi-phase samples with very different chemistry is kind of, you know, the between that, the two multi-phase ones here is kind of the target audience for this guy. And of course, you who out there who've never used EBSD, I hope you use this as a learning experience and realize that there are plenty more webinars out there to teach you what to do, and that's kind of why I do these. So again, that's pretty much what I expect. So what about these multi-phase samples? So this is data that Purdue Domain has collected at the University of Arizona, and a little bit about these patterns. So this is a geological sample. Here I can see this is the same patterns as collected from the same run. On the left, I have ankmanite. On the right, I have what's called spinel. And I can see on the left that the low symmetry material, I need basically lower symmetry lines, so lower lines for it to actually index better. That's probably not indexable on the left. On the right, perfectly indexable. But if I look at the contrast of these, why is this contrast so different? I've already kind of hinted at this, but it's going to be the scattering coefficient. So here I can see the differences of my patterns between aluminum, in this case a low Z material, which is tantalum, which is a higher Z material. And I can see that from that, the tantalum basically has just a higher signal strength. So this is pretty common in multi-phase samples, where again I have this difference. And as we already said, the static background, you know, is going to help us here. But at the same time, if I have a static background I'm using on the same material, I'm going to get, maybe less contrast in one phase than I need. And that's kind of what's happening here with the, let me go back one here. That's kind of what's happening here with the angular night is that since my sample is multi-phase, I'm getting some of my stronger background from some of the spinel areas. So basically over subtracting and getting less contrast with the angular night. Now, again, with a multi-phase sample, you can see the differences between the average pattern and the two phases here, where the one is a little bit more flat field on the left and on the right. Now, if I had a microstructure like this, I can often use the chemistry to help differentiate them, and then go ahead and use the background for each phase separately. Now, this is going to start getting to the power of this whole this partition-based approach. And again, I can use the chemistry as a differentiator, either using chi-scan or partitioning functions, and then I can basically use that and change this to what I want. But again, with these averaging signals, finding a camera setting that works well for both of these can really take a lot of time and effort. And again, sometimes I got to start and then I got to restart. But again, I can actually do just this. I can use these partitions functions in OIM analysis to partition basically by any sort of value that I have. I can use EDS counts. I can say if it's greater than something or less than something, and somewhere in between. I can use the CI values. This would be really kind of neat. I can basically pick and choose the bad data points and then reindex just those. I use the image quality to find areas that have worse patterns and settle with those. I can play with the fit if I want to. Basically, any of the partitioning functions I have, I can use them to basically help me kind of do a better background from the material. So I want to quickly, not really quickly, I'm going to walk us through this on how I do this on a geological sample I was playing with recently, which I think is a good example of this. So here is the EDS-based approach. So again, this I'm using EDS data that I've collected at the same time. So here I've, look at the sample, and I can see that based on the EDS, I have 3 distinct phases. Now I can use my mouse and fly over these different areas to see what values I'm given. And if some of those values that I'm given, I can go ahead and basically figure out what my cutoffs are between the phases. So here you can see that I can look at this. So in the bottom left of OIM analysis, basically the data follows your cursor. In this case, I'm going to be looking at specifically EDS counts. In this case, I believe it's an iron map, so I can go ahead and use the iron as my differentiator. So now I basically mouse over my sample, figure out what my cutoffs are. In this case here, I can see the color coding. It says the EDS is 77 counts for iron. So here I've chosen 3 different values. I've chosen greater than 100 for one. I've chosen, we got arrows, the less than 100. I know math. It can also be, I've chosen another one from greater than 100 to less than 300. And then finally, I've chosen to greater than 300. So now basically, again, I've chosen these values based off of, in this case, just kind of what I saw by mousing around. And now I basically have to start partitioning. So in this case, to partition, I would go ahead and right-click on the data set, and I would say New Partition. This lovely map here, this lovely pop-up window would show up. And again, I can basically do this with any one of these values. And of course, full Boolean logic is actually built into this. So if I look at this, I can see that I can use grain size properties if I want. I can use phases on different data, again, things like IQ or even video signals. Also, you can see that I have custom values. Again, we've actually added quite a few correlating with my cross-view tools in here later on, and you can actually start using those, but that's not quite out in the public yet. In this case here, I'm using the iron map. So I go ahead and click on EDS and then choose iron. And then from that, I basically have to say the values. So in this case here, I'm doing less than 100. So you can see less than, I click on that, and I do 100. And I go ahead and basically add this to the partition and look at the partition itself. And here's what I have. So now I can see I have just a data set of just the low iron areas. I go ahead and repeat this. For the next one, again, it has full Boolean logic built into it. In this case, I am doing greater than 100 and less than 300. So now I've kind of measured it in and kind of gone in and chosen exactly what I want. And here's that data set. Now, if I wanted to in this case, and if I really wanted to, I could kind of try to filter out this little bit of a lighter area if I needed to. In this case here, if I wanted to, I could, try to choose its value a little bit better, but I just didn't feel like I needed to. And here is the high iron areas. So in the end, now that I have basically these 3 partitions built up, I can go ahead and choose the partition that I'm looking at. So here is the low iron area. And I can go ahead and basically choose my phase. So here I have my phase list, and I can say, okay, this low iron material, in this case, is going to be olivine. I can say, okay, let's go ahead and use this partition. We will only index using olivine. So now I don't have to worry about any complications from indexing from any other phases. I basically picked and chose. Now, the cool thing about this, though, is, again, I can make a specific background just for that phase. So now I basically, again, I've taken all this data, I've looked at just the one phase that I found, and now I can make a specific phase-based background for this. In this case here, I've turned on NPAR. I have then done a little bit of advanced options and picked a background for it. But besides its background, again, I can actually change the Huff. So this is, I think, one of the most powerful pieces of this partition-based approach is I can change and optimize the Huff. Each phase is by itself. So, okay, this is olivine. It's lower submerged material. I need more actual lines. So here I've gone, okay, more lines. So if I'm doing a simple cubic material, I can use 6, 7, 8 lines, usually around 7 or 8. In this case, maybe the phase is weak itself. So I actually can lower the minimum peak magnitude to help it better find the lines, or basically anything else I can think of based on the different partitions. So again, now I pick and chose not just the background, but the Huff for that specific phase. So again, now I'm choosing exactly what I need to get the best data for that phase by itself. And of course, I can see what these results look like, see how it does its job, and go from there. So here I can see that I have a good CI, a good fit, plenty of votes, it's doing a good job. I'll go ahead and let it run. Now to actually get it to run, I have to be the bottom on the bottom left over here. I can see that I have my options of how much do I want to reindex. So I'm going to go ahead and zoom in on these guys. So again, bottom left corner over here. Let's go ahead and zoom in on these guys. And here I can see what my actual options are for reindexing. So I can have a single point. If you really want to for a data set, you can pick out individual points and reindex them by yourself. I would suggest you not do that. But you can if you have like one single bad data point is kind of sticking out and you want to do it. I can reindex the whole partition itself, or I can do a batch process. Now, the other thing I can do, of course, is I can actually use chi-scan or batch chi-scan too. The text box there is different kinds of chi-scans. So PCA is a phase cluster analysis, basically a way of picking and choosing for you what phases you have. Or we can turn that off and click on chi-scan. You basically get to choose the values themselves. And again, I can actually use any combination of these together. I can use multiple elements from anything I want to do. But let's go ahead and look at how these different backgrounds affect different phases. So here is that sample again. Again, this is different from the data I was just showing with EDS. But again, these are the as collected using a standard background subtraction. And again, I can see that guy on the left is probably having issues. So let's go ahead and change my background. In this case, I stacked a second background subtraction on top of it. And again, now I can see that I'm getting better contrast in my image. And I'm seeing more lines and things like the Ankmornite on the left. Now on the right, man, that spin-out pattern is looking pretty. And that's one of those patterns you take off and take down to your local printing shop, get it printed, and go ahead and put it on your wall and say, ooh, pretty. So one thing EBSD does is it definitely makes a lot of pretty images. Now if I go ahead and use a different kind of background, here I'm using a dynamic subtraction. Again, I'm not doing that great on the Ankmornite. Again, I'm seeing some lines. I'm getting a little bit fuzzy. And again, the spinel's happy. Spinel's always happy. It's nice cubic material. Now if I use a dynamic division on the Ankmornite, I can really kind of see a lot of the lower order lines, and I'm starting to get much better contrast than the other ones. And let's just go ahead and look at all these guys together. Here we can see the different patterns and how they look next to each other. So what the big thing to realize here is that what is best for the phase on the left might not be best for the phase on the right, or the other way around. So I need to go ahead and, basically, I no longer have to pick and choose at the beginning of my sample what works for everything. I can actually pick and choose what works for each phase individually. I got a question here. How do you choose the Huff parameters? Can be done after the scan is done? Yeah, so let me go ahead and find a good jump back to. So I'm going to go ahead and jump back to the slide here. Now, the Huff parameter is going to be changed in the top right. So yeah, the big thing here is I can change the Huff parameters after the scan is done. Now, if I'm doing a scan, like on a single phase sample, you always want to set the Huff up to basically do its best job anyway, right? So if I'm doing a multi-phase sample, again, honestly, nowadays I'm not even indexing a lot of multi-phase samples as they run, unless I can, it's a lot of samples at the multi-phase, I can usually find a good area and get the data I need. For my more difficult samples, I'm actually not even indexing them anymore. I'm just indexing them later on. But here to actually change the Huff settings is going to be the top right. So I think the Huff is F5 also, so you hit the F5 key, and it'll bring up the menu. But again, the pull down in the top right has got things like image processing, calibration, add or remove phases, your solutions, and a couple of different options in there. But those are all built into the reindexing window. And again, if there's some steps in here that I can take up some steps I've kind of skipped on the way. The reindexing webinar on our website has a little bit more of the details of what I would call the more basic reindexing things. And that will cover what I would say would be kind of more of like part one of this, the basics of how to reindex. Now this guy is kind of working on a little bit higher level reindexing kind of things. Let's go ahead and jump back to our patterns. Here's our patterns, and again, you can see that the different backgrounds in this case give us much different results depending on the phases that we have. Now, luckily for us, the spinel can be again relatively easy to do any of these patterns on. Why, of course, the anchornites having more issues. Now, I can also do this based on what I call the CI approach. Now, if you have OIM analysis, the data set I'm playing with here is what I call the high gain nickel data set. So if you have it, you can basically play with this and do this by yourself. And again, I'm just going to restate this because it can never be said too much. We have, most of these methods require patterns. So you really want to make sure you're saving the patterns with this. So this is a data set that we collected. It's very, very noisy, has much speckling to it, and overall has very, very low CIs. Here again, the average CI is 0.14, which again, from the general data set isn't that great. And also the fit is really poor because again, it's very, very high noise. The Huff is having issues finding the lines. Because of that, your data quality is suffering. So again, a very, very noisy speckled data set. What can I do? Well, what I can do in this case is, first thing I would do is I would run CI standardization. CI standardization is something you should almost always do. So I'm going to talk a little bit more about this. So CI standardization basically makes sure that I don't throw away pixels with the correct orientation. What it basically does is says, okay, if my neighbors have the same orientation as me within some tolerance value and has a lower CI, well, I want to make sure that I'm not throwing away those lower CI areas. So I'm going to go ahead and change this from these values to a higher value, so it's not being partitioned out. So here I can see the big red grain as our kind of our baseline. The red grain, I can see that again they all have the same orientation, or very close to it. But the CIs go from 0.0 to 0.7. Why? My pattern might be slightly different. My Huff might be finding a slightly different line, or maybe even a wrong line. But in the end, I still have the same orientation, which means I should be pretty confident that it's correct. Because of that, I'll take those lower CIs, in this case the 0.0s, 0.4s, and all the other guys, and standardize them to be the same. So now I can see that on the grain scale, all these guys basically have the same CI. So if I use that CI partition method, I would not be throwing them out. Let's go ahead and do this now. So here, again, I would basically do the same thing. Right-click on the data set level, click on New Partition. In this case, I would partition based on CI, and again, I usually use greater than 0.1. In this case, actually, let me backtrack there. If I'm looking at the data afterwards, I usually throw the bad data out, right? So I say, okay, get rid of the 0.1s, anything less than 0.1. In this case, I actually want to look at the bad data. So I'm going to say, show me the ones that are less than 0.1. Again, I chose that 0.1 value because it's kind of the value where, again, we start to change the curve on our indexing results from 90% correct up to 100. Anything less than that, again, is the ones I have to start thinking about. So in this case here, these are the points that are the bad ones. Again, I can see they're not that great. Again, very, very speckly. Some of them are just not, not what I want a data set to be like. Now I can go ahead and load the patterns. So in this case, this could be the little Kikuchi ball. So it looks like a little Kikuchi pattern in 3 dimensions. Go ahead and click on that. I go ahead and click on my data set. It says creating static background, and it's actually loading the data. Now, in this case, I almost always will right-click on the right side and click on what's called Flexi View. And from Flexi View, I'll do what's called an EBSD pattern flyby. And what this allows me to do is basically show the patterns where my mouse is. So I can go ahead and wave over the entire area and actually show what the patterns look like as I go over it. And again, now I would start working through this. So I go ahead and find an area. I go ahead and click on a pattern. And it's going to load that pattern into the software here. So again, here's my general window. Here's my image processing on the right. And I'm just going to start basically playing around with the settings, including the Huff, to see what I can do. So now I have to go ahead and turn on NPAR. I can see it's better contrast, better, less noise. I go ahead and throw a background on top of that. Or in this case, I can turn NPAR off. And you can see just a static background. It's not enough. Oh, oops, actually, let me go back real quick. This is the data set background correction. Now, this is something I should probably touch on. So here I can see I have both what's called a data set background correction and a partition background correction. And they are different things. So now, sometimes the partition is going to be the entire data set. So I haven't partitioned anything out. The data set background correction and the partition are going to be the same. But now, again, if I made different partitions, this is how I choose to make sure that I'm choosing just that partition to make my background off of. So I can either use a static background from the entire data set or on the individual phase, or you can use both, but usually you want to use one or the other. And again, this case is the partition backgrounds are pretty much the same. In this case, I think it actually is the same because I don't have a partition on. There's a dynamic background. Again, you can see the relatively flat field, not much there. But in the end, I also have these things like auto brightness contrast. But usually, again, I have way more options to play with, and you can go ahead and play with these. And there's a ton of them, so I can't really cover them any amount of time. So I'll reiterate what I said and say just sit down and play with the advanced options to see what they do, what they don't do. Again, remember, order does matter. If I do a division before subtraction, I get different results if I do a subtraction before division. And in the end, this is kind of what I tend to use for most things. Is I use NPAR and either a dynamic, a data set or a partition-based background, depending on what I'm doing. And here you can see that's exactly what I'm doing. And then I go on the bottom left there and choose what I want to do. Now, this right here is going to, again, this is what I want to do here. I can change our partition back to basically turn back on the good points. So again, remember here, I basically chose the bad points by doing a partition. I re-indexed them, and then I basically turned back on the good data points. So I pulled out the good or bad ones, redid them, and basically put them back in using partitioning. And here I can see that the partitions is, basically did a really good job, the partition-based approach. It's more, I have more precision noise point to point because, again, I basically pick and chose each individual data point by itself and basically put that individual data point back in. So sometimes you can see them, quite strongly, but again, they're better results than you had. Of course, there are some discontinuities and small details like twins. If you look at the big blue grain on the bottom, there's a single red speckle in there. that's a twin that's been lost. Now, here is basically if I ran the whole thing through it. Here's the full map, so I didn't actually partition anything based out. I just got a question in here I need a clarification on. It says, yes, please do. So I think I said something, asked a question, and then I'm missing the context there. So if you can give me a little bit of clarification on that, I'll try to make sure I answer your question. So here's again the full map results. Again, I ran the full map all at the same time. You said, you know, in this case, I've actually changed more orientations. I basically reindexed every single point versus the partition point basis, which it only indexed the points that I basically chose to do. So now, is this good or is this bad that I've changed every single orientation? It kind of depends on your philosophy. I like a whole different debate, but we can talk about that a little bit later on. The whole thing I always say is when I'm reindexing something, I'm going all the way back to first principles. I'm going back to that initial pattern, then I'm redoing the image processing, and then I'm redoing the indexing. Now I'm basically doing two different things here. I'm picking and choosing points versus doing the entire area again. Is that good? Is that bad? Which is a better philosophy? I honestly don't know. But one of the things with the four map results is it tends to be a little bit more continuous. You don't see areas that look like you picked out a point, reindex it, and put it back in. It tends to be smoother. It looks better. But again, you can also see small details can be better preserved than the individual point way. And again, to just kind of show these side by side. Again, some of the differences are subtle, but they're there. So kind of in a summary here, you know, there are many background corrections available. You know, there are many of these. You know, on good patterns, the background doesn't really have all that much difference on indexing success versus each other, but it will, of course, modify how the IQ map looks. On poor quality patterns, like due to deformation or topography or different phases, a combination of fixed subtraction or division with a dynamic correction gives better indexing results. It smooths the intensity gradient over the whole area and gives the Huff basically a better chance of finding the bands. And of course, I can also use things like intensity normalization or automatic brightness contrast to really kind of make it pop out. And again, averaging patterns over a large area helps improve the indexing success rates on rough samples. But of course, multi-phase samples may actually require treating the background separately for each phase, which you can now do pretty darn well inside of OIM Analysis 8. So again, I said this before, is how does it really change how I collect my data sets? And the way it's kind of changed it is, again, on complex samples now, I'm routinely not collecting with any backgrounds or just a static background to start off with. So my whole workflow would be to create and use a background that seemed to work for everything at the same time and basically say, okay, I hope this holds true, you know, for my entire run. And I usually would revisit my scan partially through to see if it's working how I expected it to. And I would basically either choose to let the scan go and say, okay, this is doing the job I want, or I'd quit it and restart it and losing time. Again, now because I have these partition functions built inside, I can go ahead and make a background for each phase to increase the quality of my data. Now, the other thing here is on low symmetry materials and multi-phase samples, the main checkpoint is actually to be the indexing speed itself. So if I had, you know, 5 phases loaded up, I had, you know, very low symmetry materials, this can actually slow down the whole process, where again, the indexing becomes a choke point. So now I can just not index it and just collect my data faster, and why basically waste the time anyway if I'm going to end up using the chi-scan or NPAR after the fact. Again, on easier samples, I'll still use the standard background subtraction, and because it does the job. But if I need to, I can go back and tweak it if I need to. But again, if it's a good, easy sample, I don't need to do this. And again, the main thing is also, I didn't even talk about this in this presentation all that much, is that the reindexing and background routines are causing me to move further and further away from using the older cleanup functions. So there are different ways of using image processing techniques to change orientations based on non-indexing results. So I can say, okay, my neighbor has a different orientation than me, or all my neighbors have a different orientation than me. I'm going to change my orientation based on just that. Now, I think it's often better to not use a cleanup routine nowadays, and instead I'll re-index it and get an orientation for that pixel using the actual data itself, going back to first principles, than using the image processing techniques. And then again, I really think you guys need to sit down and play. Use these functions to understand how they change the patterns and the data quality for your sample types, and then learn what you can do from there. So now with that, I'm going to open it up to questions and see what we have. On slide 56 and 57, the question is how can I trust an orientation with a low CI? That's actually a really kind of a good question. So let me go ahead and choose a slightly different slide. I think this is the one I want. So, just give me a second here. So, how do I know that something with a low CI may be correct? And it's basically, I guess one way to think about it is peer pressure, right? So if all my neighbors have the same orientation than me, but I'm less confident in myself being that orientation, I should feel better about my low CI being much higher because the other guys next to me have the same CI. Go ahead and switch to this slide real quick. So again, I have the same orientations. That 0.7 CI is basically, anything over 0.2 gets very asymptotic next to 100% correct. So again, at 0.1 it gives me about 90%. 0.2 is very asymptotic, 100%. And I probably should add that slide in here to some of the other talks, where again, even with a 0.0 CI, it's still on average more right than wrong with the orientation itself. So again, it's kind of a numbers game of saying, okay, again, my orientation to my friends is the same in my same grain. Let's go ahead and change my CI to be higher. And again, that's why I feel comfortable using something like the grain CI standardization to change those values and go from there. Hi, I got a question about the workflow. It's actually a really good question. I would say that there's not an easy process map kind of for the workflow, but definitely is a good idea for us to probably put together and work on. That'll be on my to-do list, I do believe. Very difficult question here about IQ separation of bainite from martensite. It's very complex since the dislocation densities is smaller. What is my suggestion to manage it? I think that's one of the questions I believe we have a technical note on that, and I will actually a paper on that, which I'll send out to you. It can often be a combination of IQ and other values to do that. I'd also tell you to play around with Prius. Prius gives us quite good results on things like that. And then I have a question here on what exactly is a division doing? Okay, it's actually a really good question. So let me go ahead and give me a second to skip back to the slide that kind of shows the difference here. It's quite far back, so a lot of furious clicking going on over here. So a dynamic background is a little bit different than a static background. A static background averages the patterns over a large area together. And then from that large area, it does it basically subtracts that background from each pattern itself. So I have one static background that I'm doing on each pixel. I'm using the same background. The dynamic background, I'm doing a little bit different. Instead of using the same background, I'm using the pattern itself. I'm blurring that pattern, and then I'm either subtracting that pattern, and then I'm dividing the intensity of these two patterns, depending on what I'm doing. So again, if I'm doing a dynamic subtraction, I'm basically subtracting the blurred version of itself from itself. Or if I'm doing division, I'm dividing them from each other, and then getting the intensity difference between them. So again, that's why the contrast tends to be much lower here, because I'm basically subtracting itself from itself by blurring it. So again, why static is I'm using the same pattern over and over. The dynamic, again, each pattern is getting its own background. That's why we call it dynamic. Let's go ahead and see. Actually, another good question. Do phases that have CL cause problems for lightly scratched phosphors? I can't say I've actually seen this, but let's go ahead and think about this. So, cathodoluminescence is basically light given off by your samples. Now, if I'm a lightly scratched phosphor, what's going to happen is that the scratch itself, the light can start to get through that area. Now, in general, it's not usually that strong that I have to matter with it. It also depends on the geometry of your scratch. Now, if you ever happen to want to scratch your phosphor screen for some reason, I would tell you to make sure it's not a line. Again, the Huff does a good job of finding lines. So if you have a phosphor screen and you damage it, try not to do it in a line. But I've never actually seen CL be an issue in any kind of major kind of way. So I don't think I would have an issue with CL. Let's see, another question here. Can we apply these operations in Ctf files? There are a couple different ways of bringing in other data formats. I'm not sure how they entirely work with patterns and pattern files. You should be able to bring in HDF5 formats currently in OIM Analysis 8 or in the very near future. It's one of those things where I'm not sure if that's released yet or not, but it will be in the way. In general, you can bring Ctf files into OIM Analysis, though. Do you have any tips on how to approach chemically similar phases? Probably one more question after this, and I'll go ahead and wrap it up. So if you have any other questions, feel free to send them now, and they'll answer them via email. But how do I would approach a chemically similar multi-phase samples? I don't know all the phases involved in advanced. This is actually a really good kind of question. So when I usually start a sample, if I don't know what's in it, which is my job is pretty often, somebody will give me something and say, hey, what's in it? I basically hunt and peck and do a quick EDS map to see what I have. So just do an EDS map by itself, but if we're really kind of close together, I might not be able to see it. So what I then need to do is, and if I'm doing EBSD, I would go ahead and do the EBSD approach. Now, if they're very chemically similar, the things that we look at is going to be things like the CI and the fit. So I would go ahead and rerun my entire map and then start pulling apart by fit and CIs and to see if, okay, certain grains that have lower fits, why do they have lower fits? They're very structurally the same. The fit is going to be a better value than the CI. What is the fit? The fit is basically a deviation between what the Huff found and what the index solution is. And it gives me a good idea of basically how close I am my index solution versus what the Huff found. Now, the reason that it could be bad is if I have a wrong phase. Now, if I'm dealing with, let's say, something like something that's cubic versus something that's very slightly tetragonal, it could be very small differences in those patterns. So the CIs can actually be relatively high, but the fit might be slightly off. And that's how I would kind of attack that is I would see if something with lower CI or lower fit, if a different phase does a better job. If it is, then I rerun the entire thing with that. Okay, so for our final question live, if we do TKD, which background correction is suitable or ideal? In general, it's usually best to use a combination of dynamic backgrounds and sometimes static backgrounds for TKD. Now, what I've been doing recently with TKD is, depending on the total, what I'm doing. If I'm doing a single phase material or a single crystal material for TKD, this doesn't really work. But what I've been doing recently is I take my microscope and I put it in a reduced area mode. So if I'm trying to do a very defined area and trying to get it so that it is, I want to make sure that I have a homogeneous area that I'm doing it on. So I click on the reduced area mode of my microscope. I choose just my sample area, make sure I'm not going over into free space around my sample, which is very common in TKD. And then I'll use that for my static background. But sometimes I can't do it. So I usually use a dynamic background division. If I can use a subtraction, I do it. And then sometimes I also would use a stretch and a normalization. Now, what I will tell you is that feel free to email me. I actually have a tips and tricks kind of PDF for TKD by itself. So go ahead and do that. So I'm actually not sure if we have my email on this slide. Go ahead and bring it up. We don't. But go ahead and I think a lot of you guys already have my email. But if you do have any questions about TKD, go ahead and shoot the applications email an email, and I can go ahead and send that to you. So again, all you guys, we ran a little bit over in time, so hopefully not too many people are late for lunch. But thanks for listening to me talk. I hope this information was useful for you guys. And from there, I hope you go ahead and have better data and really start digging into what OIM analysis can do for you, because OIM analysis is incredibly powerful. I love using it day by day. And again, a lot of this stuff, like this kind of material, is I don't think we kind of planned on it. It's just kind of in there. And you find that workflow that really works and does good data for you, just kind of jump on it and go for it. So with that, I'm going to go ahead and close this up. And again, feel free to shoot me questions, and I will answer them as I get them. So thanks all for joining us.